Welcome back to the series on topology. This video is a supplemental video for Lecture 5, which was on homeomorphisms. In that video, I claimed that there are functions that are continuous and bijective, but whose inverse is not continuous. An example of where this happens is the following. So we consider the half-open interval 0, 1 as a subset of the real line. And then we also look at the unit circle, which we consider as either a subset of R2, or we can also consider this as a subset of the complex plane. Now we give both of these spaces their respective subspace topologies that are induced either by the real line or by the real plane. Now I haven't yet defined in the course what the subspace topology is, but I'll quickly give the definition here because it's important for this example. If we have some known topological space X, and we have some subset S of X, then we can give S a topology that's induced by the topology on X as follows. So we say that U is open in S if and only if there exists some V, which is open in X, that satisfies U is equal to the subset intersected with V. In other words, the open sets of our new topology on the subspace are just the intersections of open sets of the larger space with that subspace. For example, this interval sits in the real line, and we know that an open interval of the real line is an open set in the topology on the real line. So for example, if we would take this red open interval here, that would be an open set of the real line. And now we're saying that the open set we get in the subspace topology would just be the intersection of this red set with the subspace. And in this case, that intersection is this pink interval here, which also happens to be an open interval. This definition goes in both directions. So if we have some subset of our subspace, which for consistency I'm again going to draw in pink. So think of this half-open subinterval in pink as a subset of our subspace. And now we want to ask if this is open in the subspace topology. Well, this is precisely the case if we can find an open set of our larger space such that the intersection of that open set with the subspace is our subset of interest. Now in this case, this pink set is actually open in the subspace topology. Why? Well, we can take this red interval here, which is an open interval in the real line, and the intersection of this red open interval with the yellow subspace, so that's the half-open interval, 0 to 1, is precisely the set that I've drawn in pink. So by the definition I've just given, this pink subset, regarded as a subset of our subspace, is an open set. However, the pink subset is not an open set of the real line. So this might seem confusing at first because we have these open sets of the subspaces which aren't necessarily open in the larger space. But this is necessary in order to accommodate the subspace topology also for sets that are closed inside the larger space. To illustrate what I mean, let's look at the subspace topology on the unit circle. So if we want to find some open set of the unit circle, this is easy. We just take an open set of the plane R2, and then we intersect it with the unit circle. For example, an open ball is an open subset of R2. So this red ball here. And now if we look at the intersection with our unit circle, that would give us this open segment of the unit circle. Hence, open segments are open sets of the unit circle. Conversely, if we're given some subset of the unit circle, maybe it's like a union of some segments, then this is open if we can find some open set of the plane whose intersection with the unit circle gives us back these pink segments. And here this is again easy because I've chosen open segments. We can just choose some open blobs in the plane that have intersection, well, this pink segments with the unit circle. Notice that here again we have the case that the pink segments, which are open in our subspace topology, aren't open in the plane. So in order to be open in the plane R2, we need to be able to find, for each point in the set, we need to find some epsilon ball, which is now two-dimensional, and this two-dimensional ball has to still fit completely inside the set. However, in our case, because this line segment that I've drawn in pink is basically a one-dimensional object, the ball doesn't fit within this one-dimensional object. Hence, in fact, the pink set, which is open in the subspace topology, isn't open inside our larger space. All right, so much for this short introduction on subspace topologies, which is going to be necessary for showing that certain maps are continuous or not. If this seemed kind of fast, don't worry about it. We'll be looking at the subspace topology in a lot more detail in a future video. However, for now, I wanted to describe it to you so that it's not completely unmotivated how we get the topologies on these spaces that I'm about to describe. In summary, a subset of the unit circle is open if for any point in that subset we can find a small segment of the unit circle, so an open segment that still fits completely within that subset. And the reason for this is that this small segment is just the intersection of a small epsilon ball with the unit circle. So essentially the topology on the unit circle looks essentially indistinguishable locally from the topology on the real line. The only difference is that it loops around completely. Similarly, a subset of this half-open interval is open precisely when we can find a small epsilon open interval around each point that fits within it completely, except, so there's kind of an edge case, namely if our subset includes this end here, and we're looking at the endpoint, then we're only interested in the intersection of this open epsilon interval with our subspace. So basically the epsilon interval will go out of our subspace on the left-hand side, but we just disregard any part of the open epsilon interval that's not part of our subspace. So in that case, the left end part of this half-open interval is also open. Great. So the reason we went through all this trouble of describing the topologies on these spaces is because we want to show that there is a bijective continuous function from this half-open interval to the unit circle that does not have a continuous inverse. What does this function do? Well, it wraps this half-open interval around the unit circle one time. So if we think about starting at this closed end of the half-open interval, that would be here, and then we wrap the interval around the unit circle once. More explicitly, if we think of the unit circle as being a subset of the complex plane, then we can write this as an exponential function as e to the I times x times 2 pi, where x is the variable that ranges from 0 to 1. Now from this description, in terms of an exponential function, it's clear that this function phi is continuous. This is something we can also check explicitly by looking at where the preimages of the open sets of the unit circle lie. So if we have any open set of the unit circle, which I'm just going to take some union of open segments, And these don't intersect this point where the ends of the interval meet. So it doesn't contain this point here. Then the preimage of these intervals will just be some, well, the corresponding open intervals in this in the real line. Now, from our explicit description of the topologies, it's clear that if they're open in S1, then also they'll be open in this half-open interval, essentially because the topology on S1 is like the topology on the real line. Now there's again an edge case for if our subset of the unit circle contains this point where the two ends of our unit interval meet, then the set we'll get as a pre-image looks as follows. So if we look at this blue segment, which is an open segment, and we look at its pre-image in the half-open interval, what this will be is basically it'll be this open part that comes from the top, and then also we have another open part which comes from the bottom. So if you think about bringing these two ends back together, then you get the original subset. But we've seen in our explication of the subspace topology on this half-open interval that, well, this set on the right is open, and also this end segment, which is half open, this is also open in the subspace topology. So that's just to convince you, if you're not super familiar with this exponential map, that the map phi is continuous. So it's not quite a proof because I've only showed this for these open segments, but if you have a more general open set in the subspace topology of the unit circle, then you can always find these open segments that lie within it, and then you can transport them back to the half-open interval, and they will be the witnesses for the fact that the preimage is open. In any case, I hope you are convinced that phi is continuous. Now, phi is also bijective. This is not too hard to see if one thinks about wrapping this unit interval around the circle. Basically, if we have some point in the interior, then there's a unique point to which it's mapped, and any point in the unit circle has some point that's mapped to it. So if I choose some arbitrary point, say here, then there's going to be some point in the half-open interval that's mapped to it. In this case, it would be more to the right. The only tricky part is really where the two ends of the interval meet. So here we've chosen this interval to be half open, which means that it includes the left hand point and does not include the right hand point, exactly because we want it to be injective on this point here, which is 1, 0 in the real plane. So the left hand point of the half open interval is mapped here, and the right hand point, well, isn't part of the half open interval, so there's really only one point that's mapped to 1, 0. Good, so phi is continuous and it's bijective, which means that, well, it has an inverse as a function, and the inverse just unwraps this half-open interval from the circle. However, in this case, this inverse is not continuous. Why is this? Well, to show that a function is not continuous, we just need to find a single open set in the codomain whose preimage isn't open in the domain. And our candidate subset is going to be this strange end segment of the half-open interval that's open in this subspace topology, but we saw wasn't open in the real line. So what's the preimage of this blue set under phi inverse? Well, it's basically just the image of this blue subset under phi. It's the same thing in this case because we have these functions being inverse to one another. And here, if we wrap just this end segment around the circle, what we get is the same half-open segment as part of the unit circle. But this is now a problem because we saw that, well, the open sets of the unit circle are precisely those that can be obtained by intersecting open sets of R2 with the unit circle. But now suppose there was some open set in R2 that had intersection the blue set with the unit circle. Well, this would mean that for any point in this green set, which maybe I should shade, so for any point in this green set, we can find a small epsilon two-dimensional ball, which still fits completely within the green set. But now if we look at the point here, so this point 1, 0, and we take any epsilon ball around it, so I'm going to draw it a bit exaggerated so that it'll show up in this kind of messy drawing here. So this is our epsilon ball around this pink point, but we could take any epsilon ball, even one that's much smaller. Then this epsilon ball will have an intersection with the unit circle that goes beyond the point 1, 0 in sort of the downward direction. So there'll be a little bit of the circle that's not contained within the blue subset that's in the intersection with the epsilon ball. Now, why is this a problem? Well, if we suppose that the green set were open, then there is some epsilon ball that still fits completely inside the green set, but this epsilon ball would have some intersection with the unit circle that reaches out beyond the point 1, 0. And so this intersection, so in purple, would still be part of the green set, but the green set was also chosen such that the intersection of the green set with the unit circle is the blue set, which would mean that this little extension, so the bit that goes beyond 0, 1 downwards, would also be part of the blue set. But this isn't the case, and this is a contradiction. So in fact, this blue set is not an open set of S1, and so we found a set that's open in the half-open interval whose preimage is no longer open in S1, and hence phi inverse is not continuous. Because this explanation, which had to use the properties of the subspace topology, is kind of convoluted, I'll try to give a second explanation that's a bit more intuitive and uses this other description we had of open sets of S1. So we were considering this blue set that's closed on one side and open on the other as a subset of the unit circle. Now, in order for this to be open in the topology on the unit circle, we need to be able, for any point, to find a small open segment that still fits completely within it. However, as we've seen, this point here, this point 1, 0, is the problem point, because if we take any small open segment, it'll reach out below, and then it won't be completely contained within the blue set. Hence, the blue set is not open in the unit circle. Now, this example is a little bit complicated because it uses these concepts of the subspace topology that we haven't really seen in detail yet, but I hope you can convince yourself that intuitively phi is continuous and its inverse is not, and essentially the reason for this is these problem points here, which are the ends of the interval in the real line. If we include one of the points and exclude the other, then after the preimage of this of the part that's closed will be a problem in terms of the continuity of the inverse function, as we've just seen. If we exclude both of the points, then we no longer have this problem, but then our function phi would no longer be surjective. So really, we have this trade-off between the function being surjective and the function having a continuous inverse. Moreover, it's really a good thing that there's no homeomorphism between this half-open interval and the unit circle, because we would say that topologically these things are distinct. Well, one is a loop and the other one is just like a linear segment. So in summary, if we want to have a homeomorphism, we don't only need to have a continuous function that's bijective, we also need to check that its inverse is also continuous.